Dear viewer, welcome once again to our program of Knowledge Quest on your favorite TV channel, Hope Channel Kenya. I'm glad that you are tuned and you are ready that we are going to learn together. Welcome to our study today. Our subject is physics and our topic is going to be something related to force. So I want to welcome you once again. My name is Peterson Maranga. I'm going to be your teacher for today. Now, in Form 1, we learnt about force. Force was one of the topics we discussed in Form 1, and we said there that, if you may remember well, that force is that which changes the physical state of an object. Or simply put, we said, force is either a push or a pull on an object. And this push or pull on an object came around with different or various effects. So we said that force which is exerted on an object can produce some effects on that object. Among them, we said force can change the physical shape of an object, or force can distort. It can change the shape of an object. Force can make an object which is stationary to start moving, or if the object was in motion, a force exerted on it can increase the speed of motion. Force can as well slow down motion, or if it is great enough, a force can stop an object which is in motion. Then there is an effect we said there, that force can produce a turning effect on an object. That if you exert a force on an object which is supported at a given point, then that force may produce a turning effect, or sometimes what we call a rotation about that point of support. And so that will form our topic that we are going to discuss here, an effect of force that is known as the turning effect of force. So that is where we get our topic from, turning effect of force. This is a topic that is in Form 2 physics syllabus, and as we have just mentioned, it is one of the effects of force. There we discussed in Form 1 and we said that force can produce a turning effect. A turning effect at that level was simply referring to a rotation about a given point. For example, imagine that you are opening a door or a window and you are exerting a force at some given point, and so the door is going to swing about the hinges. The hinges are in this case are the points of support, and so the force exerted there will make the door either open or close, but of course the motion will be about the points of support or the pivot, which in that case are the hinges of that door. And so the turning effect of force. So we say that when a force is exerted on an object which is supported at a given point, then that object, instead of moving away, the object may resolve to rotate. But the rotation is about the fulcrum, the pivot, or the point of support. So that is what we are discussing at this level, or the turning effect of force. The turning effect of force is called the moment of a force. So we are going to commonly talk about the moment of force instead of the turning effect of force. So the moment of force will be a very common phrase across or throughout the topic that we are having here. So I've just said that the turning effect of force is called the moment of a force. So the moment of a force is the same as the turning effect of force, that when the force is exerted on an object, the object may rotate or may move, but about the point of support. The object is not moving away, but it is rotating about that point of support where it is attached to. And we have different examples of objects which experience this turning effect. Say opening or closing a door, opening or closing a door or a window. You always experience that when you push the door, it's going to open, but as it opens, there's that point of where the door is supported, so it doesn't move away. Actually, it rotates. It swings about those hinges, and so we say that when you exert a force to open or close, then the door is going to experience the moment, or it's going to turn, to rotate about the hinges. Or the window, still the same thing. Or suppose you are having a car, or you are, let me just use of someone who is riding a bicycle, and you want to negotiate a corner. What do? There's a point where the left hand and the right hand are going to exert a force, and then you're going to just do something for you to negotiate the corner as appropriate. So that is another case when a force is exerted on an object, it produces a turning effect. Or as well, suppose you are driving and you want to negotiate a corner or to turn the car. What do? Again, on the steering wheel, there's something you do. The left hand is going to grab one part of the steering wheel, and the right hand still does the same thing. For you to negotiate the corner, you're going to exert the forces in such a way that the steering wheel is going to turn in a given direction, but that steering wheel is always supported at a given point. So the two forces of the left hand and the right hand also produce the rotation about the point of support, or simply what we call the moment of force when it is exerted there. Usually, now for us to understand easily what we are discussing here, now suppose we hold, you take a meter rule, say that one, and then on the far end of the meter rule you hang some masses from there. Let's have a mass here, and then another mass there. They are hanging on one end of a meter rule, and then you hold the meter rule in using one of your hands. So this is your hand here, and so you are holding the meter rule. Now something is going to be experienced, that if this is the hand on this end, and these are the masses hanging from the meter rule, or from the half, let's use a half meter rule for now. Now when the masses are placed very far away from where the hand is, you are holding with the hand, and then the masses are on the far end. When the masses are the farthest point there, there's a twisting effect that will feel on the hand. I think that is something you can try from your home or wherever you are, that you place some object. It can be even a stick. Take a stick and then you hang something slightly heavy, say 500 grams. When it is at the farthest end there, and then you are holding the other end, there's something that you're going to experience, that when the masses or the object is at the farthest point there is a twisting effect you are going to feel in the hand. The twisting effect increases as the object moves away from the point of support from your hand. And when you bring the masses or the object very close to the hands here, the twisting effect reduces. So you realize that the twisting effect you're going to feel if the object is suspended from that stick or the object you're having, the twisting effect varies depending on the position of the object hanging, in this case the masses, from the point of support, which is your hand. The farther the mass, the more the twisting effect. The closer the masses to your hand, the less the twisting effect. This twisting effect is what we are calling the turning effect, or what we have just called the moment of a force. Now the moment of force will depend on something, on two things. Number one, the sizes of the mass. If we increase the masses here at, suppose the distance from your hand to the point of support, call it D, is maintained, it's kept constant. If we increase the value of the masses, the sizes of the masses, then the twisting effect will obviously increase. That it will be harder for you to keep the object in that horizontal position if the masses are increased at that point. If we reduce the masses, then the twisting effect will reduce. That means it becomes less involving, or it becomes easier for you to hold the object in the horizontal position. And by the way, if the objects are heavy enough, you cannot support the object with your hand in the horizontal position. The object is going to produce a twisting effect that will not make you put you in a position to support the object, and so it goes down. But if the object are not heavy enough, the twisting effect may make you use some force to keep the stick or the object in the horizontal position. So number one is that if the masses increase, the twisting effect increases. If the masses reduce, the twisting effect reduces. If the masses, assuming now, are kept constant, but we vary this distance from the point of support to where they are hanging, if the distance is increasing, that means we are moving away from the hand. If the distance is increasing, the twisting effect also increases. If the distance reduces, the twisting effect also reduces. Now this twisting effect is what we are calling the moment of force, and now by definition the twisting effect or the moment of force is called, now we can have a definition or what we call the moment of force. The moment of force is obtained by taking these two things we have discussed: the distance from the point of support to where the masses are hanging, or the masses themselves, the value, the size, the magnitude of the masses. So we say the moment of force is equal to, or is defined as, the product of the force itself, the force applied, and the perpendicular distance. We have the product of the force and the perpendicular distance, and this perpendicular distance is usually from the pivot to where? To the point of application of the force. That is the simplest definition we can have for the moment of the force. That the moment of force is defined as the product of the force itself, and then we have the perpendicular distance from the pivot, that is the point of support, to the point of application of the force. Now if we are considering, let me have a simpler diagram for us to see. Suppose we have a meter rule, or we have a log of wood which is supported at this point here, and then we have a mass which is hanging at a point, say that position there. So we have a mass, and then we have the pivot at that point, and then we have the distance from the pivot to where the mass is hanging is d, called, say, d. So then in this case we shall say that the moment due to this mass which is hanging there will be equal to the force itself, then times the distance, whereby the distance is from the point of support to the point of application of that mass, so that distance is d. So we have our moment of force is equal to force times distance. So then what that means is, if this is the mass, we are going to change it into weight, keeping in mind that weight is given by mass times the gravitational force. So then the moment here becomes the mass that we are having times the gravitational force together, that will give us the force, then times the perpendicular distance. This word perpendicular is very important. We shall make use of it later. The perpendicular distance from the point of support to the point of application of the force. That distance is d. So the moment becomes mg times d. But sometimes we'll be given the force itself. So we, instead of the mass, will be having the force, say F. So for that one, we shall be having the moment. It will be equal to F times the perpendicular distance, which is d in that case. So this is what we call the moment of force. That means if the force is increased in this case, now if you look at that expression, this expression gives us something known as a direct variation. Direct variation implies that when the force increases, the moment increases. When the force decreases, the moment decreases. At the same time, when the distance increases, the moment increases. When the distance is reduced, the moment is reduced. That is what we call a direct variation. So the moment of a force will depend on two things. Number one, the force itself. Number two, the distance of the force between the point of application of that force and the point of support. If we could be having a force, say 2 newtons, we have an object which is pivoted here. If the object is pivoted at that position, then we have a force of, say, 2 newtons acting downwards at that position, say 0.1, and the same force acts at 0.2, the same 2 newtons. Now we realize that when this force is acting at position 1 here, the moment will be equal to the force, which is 2 newtons, times, say, d1. If d1 is from the pivot to where the force is, that is d1. Then from the pivot to where force 2 is, let it be d2. So the moment when it is at position 1, let us call it moment 1, it will be 2 times d1. When it is at position 2, the moment will be equal to 2 times d2. But from our drawing, if we look at the length D2 from the pivot to where the force is exerted, D2 is more than D1. That automatically tells us that the moment M2 is more than M1. That is why we are saying this, that from the definition itself, that moment is the product of force and the distance. When the distance is increased, even if the force is kept constant, when the distance is increased, the moment increases. And when the distance is reduced, the moment also is reduced. The same thing happens for the force, that if we increase the force, the moment increases. If we reduce the force, the moment also decreases. Now, if we have it in mind that the moment of a force is equal to the product of force then times the distance between the point of application of the force and the point of support, then we need to know the units of the moment of force. The moment of force. So the force is measured in newtons and the distance is measured in meters. So when we take the product of the two, it leads us to force in newtons times distance in meters. Then the units will be Newton meters. That means the SI unit of the moment of a force will be equal to, or is, a Newton meter. In short, or in symbols, it's written as capital N, small m. That is the SI unit of the moment of a force, simply because it is a multiplication of the force which is measured in newtons and the distance which is measured in meters. So when you take N times M, it gives us Nm. So that is the SI unit of our force. Usually now we're going to do calculations and we are going to express our answers in the Newton meters. All that we need to have in mind for us to do these calculations is this simple expression that the moment of force is given by the force times the distance between the force and the point of support, between the point of application of the force and the line and the point of support or the pivot itself. And then once we have done the calculations, the units for the answer will be Newton meters. The N is capital because newtons are always measured in capital N as a symbol for the newtons, and distance is measured in meters whose symbol is small m. So we have a Newton meter, or simply Nm. For example, if we obtain the moment due to the forces indicated on the diagram. So we have the first diagram. For the first diagram, we have an object, probably a meter rule, and this meter rule, say, is, if this is 0, is pivoted at 20. Let this be 100 centimeters. So the pivot is at 20 centimeters. And then we are told that there is a force which is exerted at the 0, and let that force be 5 newtons. Now, we need to get the moment due to that force of 5 newtons, which is acting at the 0 centimeters mark. So what do? We know that the moment is given by the force itself times the distance between the force and the point of support. Now, the point of application of the force is here along the 0. Then the point of support is at the 20. So we need the distance from 0 to 20. The distance from 0 to 20 on a meter rule, this is simply means we take 20 minus 0, we get 20 centimeters. So then our moment will be equal to the force. The force is 5 newtons times the distance. The distance in this case is 20, but now we need it in centimeters. We have 20 divided by 100. This is in meters. So this gives us, this 0 cancels with that one. This is 5 times 2 is 10. 10 divided by 10 is 1. So the moment becomes 1 Newton meter. So that is how we obtain the moment of a force. If we could be having a moment, another force acting at, say, 65, let me have, say, 90 centimeters acting here, that is, say, 6 newtons. The moment due to the force of the 6 newtons, this was due to the moment due to 5 newtons. The moment due to the 6 newtons will be equal to, still we have force times distance. The force is 6 newtons. But now the distance, we have the point of support is 20, and then we are measuring all the way from 20 to 90. That gives us what? The distance will be equal to 90 minus 20, which is 70 centimeters. So we shall have 70, but now we need it in meters. Divide by 100. This one cancels with that one. And then we have 6 times 7 times 6 is 42. 42 divided by 10 is 4.2. So the moment is 4.2 Newton meters. So for all the cases that we'll be having, we only need to know the force that is in the question and the distance between the point of support and the line of application of the force. But always having it in mind that that distance must be a perpendicular distance, not just the distance. We could be having a case, for example, let me have a diagram here. So that we see why we are talking about perpendicular distance. Suppose we have an object like this one, and then it is supported like that. Then from here to here, we have let me have the point of support is that one, and then we have the line of application of the force is that. Then we have this one here. This is 90 degrees. This is 3 meters. This is 4 meters. That one. And then we have 5 meters. 5 meters is from the point of support to this end here. Then, because this is where the force is applied, let me make it continuous. And then this force is, say, 10 newtons. We want to obtain the moment of the force due to the force of 10 newtons. The pivot is at that end there. We know that the moment is given by the force times the perpendicular distance. Now look at this diagram. We have a force of 10 newtons. Of course, the value we're going to use here is 10. There's no question about it. Then times the distance. But now this distance has to be, from the definition, we said that the moment of a force is the product of force and the perpendicular distance between the point of application of the force or the line of action of the force and the point of support. Now, if we look at this diagram, 5 meters from this end to that one, this angle here is no perpendicular, simply means 90 degrees. At times we can talk of perpendicular, we can talk of normal, or the two of them simply mean 90 degrees. Now, if we look at this line of action of the force and the point of support is there, if we could consider this distance here, this angle is not 90 degrees. Actually, it is an obtuse angle. But already we said we need a perpendicular distance, so this is not perpendicular. That means 5 newtons. It cannot be used in that expression. Now again, we cannot use 4 because 4, if we measure along this line here, this distance is not between the line of action of the force and the point of support. This is just a line along. That is a distance along the line of action of the force. So then, the perpendicular distance between the line of action of the force and the point of support, that one, will be, if that is 90 degrees, then we need this one here, 3 newtons. So we shall have times 3 meters. So we have 10 times 3, we get 30. So the answer becomes 30 Newton meters. So for all the cases then, we strictly need the perpendicular distance between the line of action of the force and the point of support, not just distance. As much as we're writing in the expression that we have force times distance, always have it in mind that this must be a perpendicular distance and not just any other. The perpendicular distance between the line of action of the force and the point of support. If we have it, then finding the moment of a force is not a problem. We do a multiplication, then we get the value. So in short, that is what we call the moment of a force. Now if we look at the cases of the doors and the windows, the question someone might be asking you, why are the handles placed very far away from the hinges? Very far from the hinges, actually at the farthest points. Why do we have that case? Now, for us to open a door, for example, if this is the door and we want to open that door, the hinges are here, this is the wall, and so you want to open and close it. The handles will be on the farthest point somewhere there. So for you to open or close, you only need to exert a force here at the handles, and so the door is going to swing about the hinges as you open or close. Now, knowing that the moment of force is equal to the product of force times the distance, that means because the force is going to be exerted on the hinges at the farthest end here, then the perpendicular distance between the line of action of the force and the point of support will be this one here, from the line of where the hinges are placed and the handles. So when the distance is increased, then this perpendicular distance will also be increasing. When the perpendicular distance increases, the moment increases. That means we can use less force in opening and closing the door. If the distance is too short, a lot of force will be required to open that door. If the distance is big enough, then we can use a relatively smaller force to open or close the door. So then, an application of this moment of force in the windows and the doors is in such a manner that the handles are placed far away from the hinges, so that the moment can easily be increased by increasing that distance. That means we can use a less force or a small force to open or close the window, because already the distance is large enough to produce the turning effect with a small force which is going to be exerted there. Now the same thing happens for the windows and the other applications. You realize that for most of them the distance will be increased so that a smaller force is going to be used to open or close. Actually, if we exert a force on the hinges themselves, even if the force is very big, we cannot open the door. You just make a trial there at home or wherever you are, exert a force on the hinges and try to open the door. Even if you push with a tractor, it's not possible. You cannot open it, simply because the distance at the hinges will be zero. So however much the force will be big, the moment will be zero, so it will not have a rotation, so the door cannot open. That gives us a brief introduction to the moments of force. We're going to have a short break. When we come back, we're going to talk about the principle of moments, and probably it will lead us to the end of that topic. So we're going for a short break. Stay tuned until we meet again after the break. May God bless you. Dear viewer, I'm glad that you are still tuned to our program, Knowledge Quest on Hope Channel, your favorite channel. I'm glad that you are still there. Welcome back. We proceed from where we stopped before the break. We were talking about the moment of a force, and we discussed and realized that the moment of force is the product of force and the perpendicular distance between the point of support and the line of action of the force. So we looked at an application of it in the case of the doors and the windows. We realized that the hinges and the distance between the hinges and the handles is as big as possible. Usually the handles are the farthest ends from the hinges, simply to increase the moment of force, meaning that you can use a relatively smaller force to open the doors. If the handles are very close to the hinges or at the same position with the hinges, then it may not be possible to open the doors. That is just an application part of it. So now we are going to build on this and talk about the principle of moments. So we are here now, the principle of moments. Now in the principle of moments, we are going to advance the number of forces we are considering on a given object. When we were talking about the moments of force themselves, we were considering a case when we are having only one force exerted on or applied on an object. Now, suppose we have more than one object acting on a given, more than one force acting on a given object, then how will the moments relate to one another? The moments due to each of the forces on that object. And we can do it as an experiment, kind of. Now we need some meter rule, a uniform. Actually, we need a uniform meter rule, and then we have some masses. and a knife edge just for balancing the meter rule. So we have these three things. Now we are going to do this. We balance the meter rule on a knife edge at its midpoint. So we have a meter rule horizontal, and then we have a knife edge there. We have a point of support. So this is 50 centimeters mark. That is 100 centimeters mark. This is the 0. So we balance the meter rule in such a manner. Now what we do, we take from the masses that we are having, we take one of the masses, so we place on the meter rule at a position, say 10 centimeters mark, and then we take another mass, not necessarily of the same size. We place from the other side, so this becomes our mass 1, and so we place another mass from the other side, call it mass 2. Now if we fix mass 1 at 0.10 centimeters mark, the second mass is not going to have a fixed point. What we need to do, we place it on the meter rule and we adjust its position. We can move it towards the 50 or away from the 50 until the meter rule balances horizontally. So that is the experimental part of it. So we are going to fix one of the masses. You can choose to fix mass 1 or mass 2 at a given position. Say if we fix M1 at 10, the experiment part of it will be we place M2 from the other side of the pivot, but now we vary the location of M2 until the meter rule balances horizontally. Say it is at a distance x, so that we have from M1 to 50 is D1, and from M2 to point X here will be D2. Now what we do, we take the moment of mass 1, the moment of M1 will be equal to weight 1 times D1, whereby weight 1 is equal to the mass 1 times the gravitational force, because mass can be converted into weight by taking the mass times the gravitational force, and the moment of M2 will be equal to weight 2 times D2, where again weight 2 will be equal to mass 2 times the gravitational force. Now you realize every other time that every moment the meter rule balances horizontally, then the weight 1 times D1, that is the moment due to M1, and the moment times the distance between M1 to the pivot, and the moment due to M2, that is weight 2 times the distance from X to the pivot, will always be equal. So at balance, when the meter rule is horizontal, then we have weight 1 times D1 will always be equal to weight 2 times D2. Now this leads us to a conclusion that we call, or that is known as the principle of moments. We can as well do the same by increasing the number of masses. We can choose to have another mass somewhere there, call it mass 3, and then we have another one somewhere here, mass 4. Now later we are going to get to that one, but for now let's use this expression that if the meter rule is under action, now there are two masses. Unlike in the other discussion we had only one, we have mass 1, we also have mass 2. Mass 1 has a weight 1, mass 2 also has a weight 2. So we find the moment due to weight 2, which is equal to weight 2 times distance 2 from X to 50. Then we have the moment due to weight 1, which is equal to weight 1 times 10 to 50, that which is equal to D1. Now at balance we shall always discover one thing, that this moment due to mass 1 and the moment due to mass 2 is equal. So if that is the case, we have the following as a principle. We say that for a system which is in equilibrium, that word is very important. That system must be in equilibrium and under action of a number of forces. Under action of a number of forces, then the sum of clockwise moments will be equal to the sum of anti-clockwise moments about the same point. That is the definition of the principle of moments. That for a system which is in equilibrium, under action of a number of forces, the sum of clockwise moments will be equal to the sum of anti-clockwise moments. I'm going to explain why what we call clockwise and anti-clockwise moments. Ideally, it's what we have just written in this expression, that the sum, when we had only one mass on the left-hand side of the pivot and one mass on the right-hand side of the pivot, we had weight 1 times d1 was equal to weight 2 times d2, so we had 2 moments. Now, if I choose to have this diagram here, so that I have a point of support, we don't have to put it at the center. So this is the pivot, P, and then we have one force here, force 1, acting downwards. From this one to that one, we have D1. And then I have another force, call it F2. From the pivot to F2 is D2. And then it happens we have another force, say F3. So that from the pivot to F3 is D3. Now in this case we have something here. This force 1, assuming these two forces were not there, assuming they were not existing on that diagram, if you exert only force 1, it will make the rule on the left hand side to turn downwards. As it turns downwards, on the right hand side it goes up. Now if we complete, this is downwards, that is upwards. If we complete it in a circle, we'll be having this kind of a rotation downwards, there it goes upwards. This is anti-clockwise. Anti-clockwise. Now if that is the case, then we say that the moment due to F1, because it is producing an anti-clockwise rotation, the moment is called an anti-clockwise moment, which is equal to force 1 itself. The distance between force 1 and the pivot is d1. So we're simply calling it anti-clockwise because it tends to produce an anti-clockwise rotation about the point of support when it is applied there. Now, if you look at F2 and F3, assuming this was not there, now we exert F2 there and F3, assuming the point of support is P, then F2 will make this side of the meter rule to go in the opposite direction. Now, that end will come down, and this one will go up. If we complete it in a circle, this will be, this goes down, that other side goes up. So this is a clockwise direction of rotation, unlike the other one. So then F2 and F3, both of them tend to make the rule to rotate about point P in a clockwise direction. And so we say that now the opposite of the other one is we have the clockwise moment. Now we have the moment due to force 2 is F2 times D2, but now even F3 is producing a rotation in the same direction, so we have a summation. So we have F3 times D3. Now look at this. For the moment of force due to F1, the direction of rotation it tends to produce is anticlockwise, and so we call it an anticlockwise moment. That moment is given by force times distance. The force is involved is F1. The distance from F1 to the point of support is D1. So we have D1 from F1 here to P. Then the other forces, F2 is producing a clockwise rotation, so we call its moment is a clockwise moment. That moment itself is F2 times from the point of application of the force to the point of support, which is D2. And then we also have D3, which produces a rotation in the same direction as F2, the clockwise. So the moment due to F3 is F3 itself, the force, times the distance from the force to the point of support, D3. So if two forces are producing a moment in the same direction, we have a summation to get the total moment of the clockwise rotation. So that is why in the principle now we said that for a system which is in equilibrium, under action of a number of forces, then the sum, now in this case the forces, we have force 1, force 2 and force 3, there are 3 of them. Then the sum of clockwise moments will be equal to the sum of anticlockwise moments, but then it should be at about the same point. You will realize that for all the things you have written here, all the distances are measured from the point of support, which is P. D1 is from P to force 1, D2 is from P to force 2, D3 is from P to force 3. All the distances must be measured with respect or relative to the same position, the same point. So if that is the case and the system happens to be in equilibrium, then the principle of moments will hold. Then we can state the principle. We say that for a system which is in equilibrium, under action of a number of forces, the sum of clockwise moments will be equal to the sum of the anti-clockwise moments, but then about the same position. When you are mentioning or giving that principle, the key points are a system which is in equilibrium. Of course, under action of a number of forces, the sum of clockwise moments will be equal to the sum of anti-clockwise moments about the same points. These three things must always appear: equilibrium, a number of forces, about the same point. That is when we talk of the principle of moments. Equilibrium here means this system is horizontal. It is balancing horizontally. It is not rotating. It is in a state of balance. So it is balancing horizontally. It is not rotating either clockwise or anti-clockwise. If the system is rotating, say anti-clockwise or clockwise, then the principle does not hold. So the principle is only holding if the system is in equilibrium. We do an example that applies this principle of moments. The system shown below is in equilibrium. That is the statement part of it. The system shown in the figure below is in equilibrium. Then the question is we find the value of F2. So we have a system like this one. We have that it's on a meter rule. This is 0. The point of support is 20 here. So we have at 0, we have a force of say 10 newtons. So we have at 30, we have a force of 2 newtons. And at 40, we have another force F2, which we do not know. And we want to look for the value of that F2. So what do we do? We shall say, let this be 20 here. So we shall say that now if we look at these 20 newtons and the 2 newtons and F2, about the point of support, 20 will tend to produce a rotation in this direction, in the sense that it makes this end to move downwards as the other one goes up. This is an anti-clockwise rotation. So that means the moment due to 20 is an anti-clockwise moment. So we say anti-clockwise moment in the question will be equal to only the force of 20. So we have 20. The distance from 20 to the point of support is 0 to 20, which is 20 itself. So 20 divided by 100. This gives us 4 Newton meters. Then we have the clockwise moments. For the clockwise moments, we're going to have a summation, because 2 and F2 will both tend to produce a rotation in the same direction, in the sense that they'll make this part of the rule to go down as the other one goes up, which is a clockwise direction. So the moment will be equal to the moment due to force 2, which is 2, times the distance from force 2 to the point of support. We have 20 to 30. The difference is 10. 30 minus 20 is 10. So we have 10 divided by 100. This gives us 0.2 Newton meters. Then in addition, we have plus the moment due to force 2. We have F2 times the distance from the point of support. The point of application of that force is 40, from 20 to 40, which is equal to 40 minus 20. It is 20. 20 divided by 100. This and that one, it gives us plus 0.2 F2. Now we want to find the value of F2. We now go back to the principle of moments. We say that for a system which is in equilibrium under action of a number of forces, the sum of clockwise moments about a point will be equal to the sum of anti-clockwise moments about the same point. So we shall equate the clockwise moments, which is 0.2 plus 0.2 F2 is equal to, the anti-clockwise moments is only 4, so equal to 4. So we like terms together. We take 0.2 to the right hand side. We remain with 0.2. F2 is equal to 4 minus 0.2 is 3.8. So then our F2, 0.2 F2 is equal to 3.8. then our F2 becomes 3.8 divided by 0.2. This is equal to 19 newtons. That is the value of F2. And for us to get the value of F2 there, we have made use of the principle of moments. So then the principle of moments is in this case going to be used to find the values of unknown forces in the system, or the values of unknown distances in the same system. But the basic thing is that if we know the point of support and the other forces, now it's upon you as a student to know which forces are producing a clockwise moment, which ones are producing an anti-clockwise moment. Now, if the system is in equilibrium, then we say that the sum of clockwise moments will be equal to the sum of anti-clockwise moments, but then about the same point of support. The point of support has to remain the same across in all the moments or the distances you're going to measure. You do not vary the point of support. Now, as a student, then it's good for us to know that the turning effect of force is simply what we call the moment of force. That by definition, we say that the moment of a force is the product of the force and the perpendicular distance from the point of support to the line of action of the force, that is measured in Newton meters as the SI units. And now, if a system is having more than one force, that means 2, 3, 4, or as many forces as it can accommodate, then if that system happens to be in equilibrium, the principle of moment will come to play. That if the system is in equilibrium, then the sum of the clockwise forces will be equal to the sum of anti-clockwise moments, but at this about the same point of support. Ideally, that brings us to all that you need to know concerning the turning effect of force. Maybe the application part of it is when we are exerting the forces very far away from the points of support. If you increase the distance, then less force is going to be involved for you to cause a turning effect. And if the distance is small, then more force will be required for you to produce to cause the same turning effect about the same point. Till our next lesson, I pray that you continue watching Hope Channel Kenya for more blessings. Stay tuned. In our next lesson, we're going to do an introduction to a new topic. I'm glad to be having you as my student. Keep watching. Let's meet in the next lesson. Goodbye.